In this video, we're going to show an easy simulation of an stochastic integral. What we are actually going to do is in particular, to show the simulation of this integral, which is a very popular example of an stochastic integral, which is just the integral of Brownian motion with respect to Brownian motion. So here, what we actually have is, well, let's say we are in a probability space, as always, and we are talking about a process uh, which is Brownian motion, or standard Brownian motion, or also a standard Wiener process. So what the idea is to actually can write this integral as a sum. So the idea or the trick is to write the integral as the limit of the sum from 0 to n minus 1 Brownian motion times the change. And here, of course, we are talking about a partition of the time interval, which goes 0 equal to 0 all the way to Tn equal t. And well, we could say Ti is equal to It over n. Obviously n in the naturalist. Well, in order to be able to do this, we actually have to check for a condition before, which is the continuity of the expectation of Bs times Bt. So in order to do this, but well, we know from Brownian motion that this thing we have here, this expectancy, is just the covariance of Brownian motion, which we know is the minimum between S and T. So then we have our condition met. And we know we can rewrite this integral as this sum. So now the next step is to solve all this. And we are doing this in order to have something to use as a base to compare our simulation and to know that what we are actually simulating has something that can be assuring us what we are actually doing. So in other words, we want a base to our simulation. So let's solve all these limits. So well, the first step is to actually do this product. So let's rewrite this as limit sum n minus 1 of t plus 1 squared. Okay, and now what we are going to do is to rewrite this as a following expression. So you can notice these two are just the same. You can factor it out and see that these expressions are equivalent. And we are doing this because in the next step we are going to make the sum of the limits. Well, actually, let's take the 1/2 out. Plus, well, limit all this. And then notice what we have here is just the quadratic variation of Brownian motion. In other words, we have B, T here. And we know from Brownian motion that all these, actually the quadratic variation of Brownian motion is nothing more than just T, or in an interval, let's say from A to B, the quadratic variation of Brownian motion is B minus A. So here we have T, well from 0 to T, so the quadratic variation is just T. And then we write it. And this sum that we have here is nothing more than an example of a telescoping series. So we know the result from all this is just Vt minus Vt0. And you can notice it from replacing the indexes and just write Vt1 minus Vt0, well, T0 plus Vt2 minus Vt1. So this goes with this, and the same happens with Vt2, etc., till the last term, which will be the last term is going to be Vtn. But we know from the definition of Vti that we are working with it over n. So in the last, we remain with Tn equal T. And we know this obviously from the partition we talked about before. So we remain with the limit percent goes infinity of well, not the limit, but we end with this. But we know this is just v0, and we know from Brownian motion that it's just 0. So the result is okay. Here I have I change notation. This is Vt minus Vt0. Well, this change of from B to W is because we know Brownian motion can be written as this or as with a W, because also it's called binary process, and I just here change notation, but there is no a major problem. So we know this integral is actually this can be seen as the exact solution. Well, this is just a Ito integral. And now we are going to simulate, and we have in some sense to make an approximation of this. And what we are going to use is this expression. So in order to do this, let's go to Jupyter, and we're going to work with Python. Okay. So first of all, let's import our libraries. I'll be using NumPy, but you can use our libraries. There is no problem on that. And I know there can be better implementation of the algorithm, but this video is just with educational purposes, so let's do in the following way. Let's also use a library to plot our results. So the first thing we have to do in order to simulate the stochastic integral is first to simulate our main tool, which, as you can notice, was Brownian motion. So as first step, let's simulate Brownian motion. Let's use 1000 as n, and let's do this till time 1. So let's say Brownian motion is just as we know it. The standard Brownian motion starts at 0, so let's also include that. And we use the fact that Brownian motion is normally distributed, or if it follows a Gaussian distribution with mean 0, and difference is the time length interval, the length of the time interval, and we are going to use n as steps in order to simulate Brownian motion. So yeah, and actually the function in NumPy is parameterized using standard deviation. So let's take the square root of the variation, which, as I said, is just the time over n, which is the length of the intervals we are using. And let's do a size of n. And finally, let's sum. Let's accumulate this the sum. I think I have a mismatch. Yeah. With this, we are simulating a Brownian motion. And let's take a line space from 0 to time n plus 1, as we are adding 0. Now the integral, we are just rewrite our sum, which was Brownian motion 0 to n minus 1 times Brownian motion. Well, it was actually the difference of Brownian motion 1 to n. We here have our index ti plus 1, which was in our previous solution. From motion from 0 to n minus 1, and also cum sum. and I think that it's all. So now we are simulating Brownian motion here, and simulations with mean 0 and the variance time. In this case we are taking 1 over n, and we are taking these steps, and this is just the integral as written as a sum. And now let's just plot this. And well, as I said, we are going to use the exact solution to compare our approximation based on simulation and our exact solution in some sense. So we are going to use a half times motion squared minus steps. Steps are representing our times. Okay, this goes from 0 to n minus 1. Now, steps to n minus 1. And let's use the integral. Okay, biplot is not defined out. Oh, okay, a mistake here. And here you have. Let's use some labels. Well, legends actually. Biplot, legends. Okay, so what we are showing here is just the exact, which was this 1/2 times Brownian motion squared minus the time, which is the blue line, and the orange line is the approximation we are doing with the simulation, which is actually all this sum using Brownian motion. And this is actually all. This is the integral. We can extend actually this algorithm and go further, but this is just an easy example of how to simulate the integral and approximate it using simulation of Brownian motion. And just for fun, let's also do the Stochastic integral. Just because it's actually the same way, but the main difference is from the into integral, which we were using before. In the Stochastic integral, what we take is the middle point between two Brownian motions in this case. So this is, let's do this direct. Well, no, let's call it 0.5 times Brownian motion from 1 to n plus Brownian motion from 0 to n minus 1. And well, as I said, this is just taking the middle point between Brownian motion in two steps, and this time times the Brownian motion from 1 to n minus run motion 0 times n minus 1. So this is actually the same idea we had before. We have this increment which is here, and the difference is here. In the Ito integral we take this as the representant, and in the Stratonovich class in the Stratonovich integral we take the middle point. And well, let's do a comp sum. Well, if you solve this integral, you're going to end up having just that the solution is a half times run motion squared. So the difference in solution of the integral is actually the time. In the Ito integral we end up having this minus time, but in the Stratonovich integral there is no time. It's just a half of run motion squared. So let's also plot this, and let's do it directly. So we do the same. We're using steps as well, to plot all this. As I said, the solution is a half of run motion squared. Then the same idea. I call it strat. And here you have. So this is not very clear, but we have the blue line. You can notice it in the, well, there is just a blue line here. You can notice this approach or the approximation we are doing using the simulation of random motion. In this case, it's very clear and very near to the, let's call it, exact solution. And you can notice this blue line behind the orange line, but it's not very clear, but there is it. So in this way we are approximating the, let's say, the stochastic integral in two ways. We are using here an approximation to the Ito integral, or the Ito way, and here using the Stratonovich integral. But as you can notice, actually the trick is just to rewrite the integral as a sum, and then use our tool, our main tool, which is the simulation of Brownian motion. So thanks for watching.